Can you hear me?
I can hear you.
Awesome. Awesome. Let's get going in just a second. I'm adjusting my display a little bit, and then I can write on it. Oh, the spring is a little tight today. Oh, there we go. So sharing my desktop and closing out on a bunch of other things that I have here. And opening up the notepad and going straight to chapter number 16 where we were. Yeah, this is the main exercise, which is what we were scheduled to do the other day. Where's my pencil there? So let's quickly, I'll remind myself as to what I was discussing, and then I will, of course, open the Firefox browser window, go to that window and open up the correct file there, which is 16. And I need to run through all of these guys before I can, at least some of the critical steps before I can actually run the, even though we run it, it will take a couple of weeks. So it is kind of moot, but it's important. It's important and actually very interesting to understand how do we apply these techniques to any kind of a feedback system. Essentially, if you think about these reinforcement learning, they are feedback-based, classic feedback control systems in your electrical engineering. If you think of, in electrical engineering, you have this concept of an input of some sorts, and you have some black box that produces an output, and you want to make sure that your output is a function of some input. Like you want to simulate that function, some kind of function of input, and so in here you will use your operational amplifiers or other circuitry. You will put, this is electrical engineering, by the way. So the classic way of implementing a feedback control is to bring in output and feed it as an input with a negative and a positive signal in the amplifier or the operational amplifier, which is basically not just one, but a black box. And this technique is used in many systems which are, ancient, probably 100 years or more than that, where people have been using equipment, electrical equipment that will control some output action based on some input action. And this is called feedback control. What the role of this is, basically it taps out a portion, or taps the output and feeds in a portion of that to correct, with a negative sign, to correct the behavior of this black box to accordingly, appropriately adjust to the output. And that's the classic control system, also called negative feedback control system, negative feedback control. And that is implemented in many electrical equipment, as you may have seen. I'll bring up some very clear examples to help you understand. Probably you already know this idea. The idea here is that your output that you have is immediately fed almost in real time with negative, as a negative feedback, and it is basically real time, in almost real time, I should say, almost real time. So it can take corrective action and correct the output that you expect from the system. Now, whereas if you apply this technique to any kind of generalized problem where you have a system that takes an input and produces an output, you want to get feedback, and you want to actually incorporate that into the system so that this is your system. This feedback may not be immediate. It may be realized, not immediate, so it may be realized after some time. So there is a time dependency involved here. It may be delayed feedback. And so the feedback is delayed, your action may be erratic. Your output may be erratic, a little bit, erratic, a bit. And so that is what this kind of technique is attempting to correct and control and actually learn. And so in the scenarios that we have here discussed, let's go roll back a little bit here. Temporal difference learning and Q learning, those techniques are basically mathematical techniques that simulate this idea where you have some kind of input that you're feeding into the system. This can be not just one, but a whole host of inputs from a variety of places. And you are trying to drive an output that you want to accomplish. Now, if you take of a car being driven, so like an auto car, for example, or I should say autonomous car, autonomous like a Tesla or a Google car or any kind of these things, the automatic cars that are currently being developed, some of them to a great degree of sophistication, are receiving inputs from probably many sources. And these are the inputs. And the car is taking that input and processing and producing an output. The expected output is that you want this object, the car itself, to travel from A to B on a map. So you have a map, and in that map you want the car to go from here to here and follow a specific route. So you will specify the route also, not just the map, but also either you can specify a route or you let the car itself figure out the best route. Like the best route meaning if there is traffic on this route and that lots of cars, and so it is not a good idea to go that direction, so it will figure out an alternative route, which is probably a better route to A to B, as opposed to that route, which is crowded and basically causing a delay. And you've seen this in Google Maps and Apple Maps and things like that implemented. Now, the input that you receive in a car can be, multiple things. Like that not only includes like what do you see in front of the car, on the side of the car, how many people are sitting, what's the body weight, what's the tire weight, what's the net weight, the angle, the velocity, the markings on the road, other people, other objects, other things on the road that may exist, new markings, speed signs, road construction, all the things that you normally see on a car as you drive as a person. They are all inputs. And the output that you really want to accomplish is to have this car safely travel from A to B most efficiently according to the user's desire. And this result that you want to accomplish is not absolutely immediate in real time. It takes time for you to travel from here to there. And that delay is involved because of the nature of the problem. And so this is the same thing with anything. You have a robot vacuum that is cleaning up a room, and that robot starts from here, goes in this direction or that direction. Essentially, what you want is at the end of 30 minutes, or whatever time period you set, the room should be clean. That's the output. It's not immediate output. So you have to figure out iteratively as to what course of action should the robot take to effectively clean the room in this time. Or forget the time aspect, but clean the room fastest. Or another approach is to make sure that the room is as clean as you want without making the human should not be involved. The moment you have a human user come and pick up dirt, now that's the fail. That's a negative score for the machine to perform. So performance of the machine goes a negative hit. Same scenarios again. You have a thermostat like the one I showed you, the Ecobee thermostat. So let me remind you of that setup. You have sensors here, sensor 1, sensor 2, sensor 3, multiple rooms, multiple sensors collecting, gathering information about just one factor. Let's call it temperature right now. So you have temperature variables from multiple sources, and you want to set a policy in the thermostat. So you say, 72. That's what I would like to have. And so set it at that. That's the target temperature you want to accomplish. The actual temperature may be different. The actual temperature comes from here, these values. And so you want to take these 4 values and you sum them up, divide by 4. That's the average actual temperature. And you will notice that there is a difference between the target and the actual. So your system will need to take corrective action. If the actual temperature happens to be lower than this temperature, the desired temperature or target desired temperature, then you want to essentially turn it on, turn on the furnace. And furnace will eventually heat up your whole home. As a result, these temp values will grow higher. The average will also grow higher. And as a consequence, you will have the actual average go up. So this difference between the target temperature and the actual temperature will reduce. And eventually it will reach the target. When it reaches the target, you want to turn it off and stay like that. And the moment the temperature will fall by itself, you will again turn it on. And you want to learn this and figure out what the need of the human is. And the need of the human can change depending on the weather outside. The weather outside can be, 24 degrees or maybe 40 degrees, or God knows what the temperature can vary during the day. And so that is another input. So the input to the system is not just these 4 temperature readings, but multiple other things. And there is one more input, which is human. Human sometimes has to come in and tell the system that, hey, system, you are stupid. Like the other day, I had this example of, one of the sensors picking up the wrong thing. And so it picked up the wrong measurement because the human wanted something different. And so it started to pick up heat from a extra heater I had in that room. And so it effectively led to a wrong average. And that is how the system is designed. So the system started behaving bad as a consequence, and I had to physically take corrective action. And that is how the system is taking a negative points, or sometimes it takes positive points for not bothering the human and automatically taking correct course of action is the reward that the system receives. Another example would be a robot. You want the robot to go from this location to that location, in the process picking up this object O. So this is the object sitting on the table, and you want this robot R to go pick up this object and then put it here, and like that. So that's the desired output. And what the robot does is that it looks around, moves around in that direction, depending on how the motion is going to be, whether it is walking or rolling or whatever that robot is, picks up the object, places it here, and done. In the process, there will be obstacles or unforeseen situations coming along, and you want the robot to eventually succeed, ideally very, very quickly succeed. And that's the nature of any kind of a problem you can think of, that you have certain inputs. You want to produce a desired output effectively, ideally, very, very quickly, based on these inputs that can be either immediately observed or observed over time, or interim output as it is fed back as an input. You want to ultimately get to the desired output, and this can be delayed. And so the delay idea is what is the concept of temporal difference learning concept that kicks into play. So the underlying concept here is that you discussed the idea of you want to have a system that learns to play golf. And so you want to have the machine player needs to learn golf. So what the machine can do is, watch a monkey play random motion, with a golf stick and a ball and whatever they're doing. And so let the monkey do random things. It'll do all possible stochastically random things that a monkey can do. And your machine player needs to look at what the monkey is doing and examine its various possible outcomes, and eventually find out what's the right course of sequences to get through all the holes that we have 1 through 18, and optimize on the output final result, which is 1 stroke at each step. And you go all the way to 18 and you're done and you win the game. Now that takes so many steps and so many variables, and you have to actually learn the thing by observing the monkey. Now the space here, space as in action space, I should say, all possible actions that a monkey can do is really large. really, really large. Monkey can do this or that, or this motion or that motion, this stick, that angle, that variety of options are available in the option space. I hope I did not lose you. Something happened. Are you still there?
I'm still here.
Okay, good. So this mode of learning is actually pretty difficult. It takes forever for it to actually finish, because the space of actions, possible actions, is very large. And so the the idea here essentially is that monkey idea. Where is the monkey? Yeah, drunk monkey. I call it a drunkle, drunk uncle. That's same idea, monkey or drunk uncle. Same idea. So the way to do that better than this purely stochastic random approach is to refine and maybe do something like we have discussed, called stochastic gradient descent. That is a slightly faster way to accomplish the final outcome in a gradient descent if you actually initially pick a small subset or a mini batch and go stochastic with that. And that's the underlying concept here. Again, in that what we are doing here is that we are using a greedy policy. This epsilon is a small number, a low probability number, and this is what the greedy policy will be different from a purely random policy, is that it spends more and more time in exploring the parts of the environment that are more relevant or more interesting to the game. And so we'll say start with some epsilon value of 1 and go it down, bring it down over number of steps, all the way to a very small number, like 0.5, for example, and iterate on that to get to a mode of exploration of the entire action space, to get to a value of the Q values, which is the value that we want to calculate, to extrapolate and figure out what actions or what set of actions will actually lead to a better outcome. So that's the underlying concept in this technique of exploration technique, in which we greedily select certain parts of the action space which are interesting, and that's the underlying idea here. So we'll see how this is implemented in a real example. And so that example is right here. And so we want to get to that example first, for which I had to initialize this sheet. So I'll begin initializing, and I'll be careful not to execute parts which are not necessary, otherwise we'll waste time. And so this is your OpenAI gym loaded. Let me zoom through this. This should be quick. And I think this should actually load up all the initial steps. So I'm going to go straight ahead to the segment, which is the area of interest. So this is your hard-coded policy. Then we apply to a neural network policy, and we saw that this cart pole is able to do a lot better than we saw before. And then we have this discussion on Markov chain, Markov decision process, and then the idea of Q learning here. This idea of Q learning is that the greedy policy. I think this is the greedy policy method. Let's go cross-check, compare notes, and I think this is the greedy policy. So compare this. What we are looking at in this function is to calculate the Q values based on 1 minus alpha, which is this one, the Q values from a previous calculation, plus alpha times the reward, the gamma, and then this is, okay, I need to go and adjust this. So I'm going to clear my ink so I can get to the other segment. I have to shrink this font a little bit to get to that point. I think this is what we are looking. No, where are we? Did I lose? A Markov decision process and the Q-learning greedy policy, which is this policy. The underlying implementation of this function that you're looking at on the left side is what you see written here in the calculation of Q values in this segment, which is what we were looking at. Q values here, 1 minus alpha and alpha, that this 1 minus alpha and alpha, reward plus gamma times next value. That's reward, your gamma times the next value. And this is a max function here built in. That max is right there. And the iteration is happening in your number of steps. So you're trying out a variety of various values, ultimately trying to find the best set of values you want to use. And that is how you're setting up your Markov decision process environment. Then you set an optimal policy as a function definition. Then you print out your Q values, and then you actually run it for the full range of 1,000 episodes. And this is more of a example calculation of how do you use this function to evaluate on an iterative basis to come up with a Q value that you need. Now we'll use these techniques to actually see how we can put this to play Pac-Man. That's I think the next idea. So we'll move over to the Pac-Man section now, which is the next one. Where is that? Pac-Man. There, it's right here. So the Pac-Man section is actually interesting in that you are really having the game play Pac-Man as opposed to you playing the Pac-Man game. So Pac-Man, as you already know, this is the game that you probably recall. So we need to basically simulate an Atari machine. That Atari is built into our AI gym, OpenAI gym. That there are some steps needed. Those are already taken care of in our notebook. They're already taken care of. So that Pac-Man environment you can just create like this, and it gives you the shape of environment as what are you dealing with. You are dealing with an input, and this 3 means the color space, red, green, and blue. And the input essentially is a picture of what you see on the screen, 210 by 160 pixels. Pixels of information. And in 3 colors, RGB. That's the input space you're looking at. The game begins pretty much like this picture. So you see something, and now you're expected to play Pac-Man. That at least the machine is expected to play Pac-Man with these inputs. That inputs, as you already have understood, is that the input is the image that you see on the screen, like this image, for example, and this one. Now this image is in color, so it is kind of pointless. Like for a machine to deal with red, green, and blue is kind of useless. Excuse me. So that is why, first of all, we drop the color information. So it's all grayscale now. So we drop color, basically reduce all the RGB information, keep only one channel, which is the monochrome channel. So that size is reduced already. The next thing we do is scale it down a little bit. So it's 160 by 210. I think I drew the earlier picture like 210 by 160. It is actually not like that. The correct way to draw the picture is 160 by 210. So it's a longish, as a portraitish image as opposed to a sorry, as opposed to a landscape-ish image. This is landscape-ish. This is portrait-y. These are my made-up words. So basically, smaller number and larger number. That's the way you have here. And you will shrink these images that are received in the input into the system that you basically, this is what you see when you play the game. So you want the machine player to take that as an input, right? The machine should see what you see, what you would otherwise see when you play. Now the machine plays. The machine has to play by looking at this image. And so the image is down converted to 88 by 80 grayscale. Let's clear my ink and understand what we are going to deal with in here. So I will adjust my font a little bit. There we go. Yeah. So here we have seen the action input space, which we understand. There are action space, meaning what can you do, like you as a player. So the machine as a player, what can the machine do? It can take 9 different actions. It receives so many different input data images, and it can take 9 actions. Now you see something, you do something, you see something, you do something. And your goal is to maximize the game score. At the end of the game, you want to get the maximum possible score ever that anybody has ever taken, superhuman score. That's what you want to accomplish. And you will play using these 9 actions on an input sequence that comes like this. And you'll keep toggling your keypad, the number pad, basically the up, down, left, right, this, that, and this, that, and a center key. That's the 9 keys you have. And you will toggle those keys around. The machine player needs to toggle them and accomplish superhuman score. That is what this program will accomplish. That's the Pac-Man environment that we loaded. And now we will see the color space. We want to, processing of the image is optional. You don't have to reduce the image size like this. You don't have to shrink. You don't have to reduce the RGB into grayscale. But if you do, your CPU cost reduces. So CPU is not, you don't need as much compute horsepower because you're dealing with low resolution imagery. And so this is your function that defines pre-processing and reshaping the image to this 88 by 80 by 1. So that's the new shape. You had a before shape was this. The new shape will be this. That's the new input. So it's a derivative input. And that's your new image. Pre-process the observation. Whatever the observations are these observations. And this IMG is this observation. So you got the observation. You can take 9 actions. And you don't get the result immediately. You get the result at the end of the game when there's a done flag. Done equals true, meaning the game is over. That's the flag. So now let's proceed. See what we can do with this game itself. I mean, how will we have the machine do the math needed to eventually accomplish superhuman score, like the best score a human can ever receive. There are, by the way, leaderboards on this. People have been playing this game since 1980s, ever since this game first came out, and this software beats all of those. That's what we'll see and how it beats, and then we'll run it, and we'll get together after like a couple of weeks to see what happens. So here we have some plotting functions. I think these are just plotting. Plot this, plot that, and plot show. So basically what we are doing is showing that this is the input and this is your output. That's just more of a show. Like, well, what are we dealing with? The modified observations. That's what we're dealing with. So we'll scroll. Now we'll build a deep Q-learning network to accomplish what we want. And this code is fairly involved, as you will see, lots and lots and lots and lots of steps. And it goes on, and then we'll eventually animate the course, animate the final result when this eventually runs. But let's see how it actually runs. So we have to understand this code. At least I don't think we can succeed in running it, but we'll see. So we'll run parts of it, at least some cycles. So begin with resetting the graph. I should also read the book on the side, so I don't miss any idea here. Yeah, this idea we already have seen. The input space or the action space, the input space here, which are going to reduce it to 88, 81. And there are 9 discrete actions: center, up, right, left, down, upper right, and so on. And so those are the actions. Observations are screenshots, reduced or shrunk and discolored, grayscale. And so let's go forward. So this is the pre-processing function, the actual images, DQN. Now how will the network look like? So let's see how we want to really create that deep learning Q value network, or deep Q learning network. That's what we want to build. So we provided an input, and we have the first set of inputs are the input screenshots from the game itself that we receive. And then we make it pass through convolution network. This is one convolution layer, another convolution, and a fully connected 512 unit and fully connected 9 units. These 9 correspond to the action you will take. So you see something, you see this, the action you take is one of 9 values. Those values are up, down, like that, all the 9 action. So you see something, you do something. You see something else, you do something else. And effectively what you really want to do is to accomplish the game score. That is what we want to maximize. It is conceptually the same type of an optimization problem, although the optimization is not immediate. You get the score, but at the end of the game, you will eventually get the score. In the process will go up and down a little bit based on a wrong action or a good action. If you do a wrong action, the score goes down. You do good actions, the score goes up. All these things matter, but eventually they accumulate into a final score. And that is what you want to maximize, the ultimate, this. You take these actions based on what you see. So you see, you act, you see, you act. It keeps on going with the ultimate goal of this. And so to come up with what action should we take, what action should the machine player take, comes from this calculation. And that is, a neural network, as we know already. So we have seen this. So we have to build this network. That's the basis of this code that we are looking at on the right side here, all the way down, all the way up to the bottom of this page. That's what is going to build this particular neural network, because that will actually come up with a proper action we should take for a given view that you see. You see something, you do something. Keep iterating to get a score. That's the game. And we are implementing this neural network right here. Okay, let's read. So reset the graph. By the way, most of it is actual setup of the problem. We'll define some functions along the way, and then use those functions to basically create a network. And then we'll initialize the session in TensorFlow and execute TensorFlow and let it run to train itself. Once the system is trained, it can play. It can play better than any human has ever played. That's the premise of the discussion. But we'll see how the reality is. And so eventually we'll get to see it. Input height, input width, input channel, so that is obvious. We are setting up convolutional neural maps of 32 by 64 by 64. This is the number of maps. Hold on, what is this about? N maps. I think we'll get to as to where exactly this is used. This is not super obvious. The convolutional kernel sizes, 8 by 8, 4 by 4, 3 by 3. Convolutional strides, 4 to 1. This piece has, I'm not clear about what that actually stands for, but maybe the book will describe. I must have forgotten it. So I'm going to erase this and scroll in the book to find out where they actually belong. The DQN designed by DeepMind requires two DQN networks with the same architecture. Okay. And one will be used to drive the Pac-Man. The other is used to build Q values. And this idea, I think, has to be understood. So let me just describe that idea first. This idea is not super obvious. So I will go to a white sheet of paper and describe this idea to you. This is the actual DeepMind game machine. So which played in 2017 and beat the champion of Go. So the idea here described is that in our discussion, the idea was to optimize a score based on the action you take, and the action is calculated based on a neural network of multiple layers, and you feed it what you see. What you do is based on what you see, and this is the ultimate goal. Now, what DeepMind found is the best way to approach this process of looking and doing and looking and doing is that if you just use one deep Q network, only one, then it is not as good as compared to if you use two DQNs. So the second DQN. And the second DQN, what the role of this is that there are two distinct roles of the two distinctly different deep Q networks. One of them actually plays and actually drives the Pac-Man like this or that or this or that. It will press the button to make it move. That the one that plays. And a separate, similar, basically identical DQN second. We'll also look at the same input, see what you see. And all it does is calculates Q values. This one plays, this one calculates. And at regular intervals, we copy the online DQN to the target DQN, replacing the parameters. The online and target DQN, there are two different DQNs here. The one is called online DQN. So this is the one that is actually playing the game as it runs. And a target DQN, which is basically doing the math, calculating the Q values. And what effectively at regular intervals, what DeepMind did in their implementation that the world saw in 2017 is that they copy parameters from here. From the online to the target, this way. And use new parameters as at frequent regular intervals. With some periodicity, you have to take parameters from this network, which is actually playing the game, copy them over to the target network that calculates your Q values. And therefore, we need to have two DQNs. So that's the underlying idea in this description. The reason that DeepMind actually describes why you need to have two DQNs is that it leads into feedback loops. That's what they have found in a feedback loop is something that basically it leads you away from where you want to go, which generates echo. So if you have a scenario where you hear in a video conference like this, if you have say for example on your end, so this is me and this is you, on your end you have a speaker and a microphone. I have a speaker and I have a microphone and a speaker. So on your end, if you somehow manage to take the microphone and put it right in front of the speaker, like right there, and you unmute yourself, unmute. So microphone is typically away from the speaker just a little bit. If you put your mic right on the top of the speaker and you unmute, then what happens is anytime I speak into my mic, this sound goes to your speaker and the speaker will speak into your mic and that mic will go fed back into my speaker. And so what I hear is echo. So you don't hear any echo, but what you hear is my spoken words and you hear it. But what I get back from your speaker is my own voice. And if I leave this running, and in my case, even my mic is closer to the speaker. In that case, my sound that I produce by my mouth, so this is my mouth, making the sound that goes captured in the microphone here that travels to your speaker, then your speaker captures, transmits to the microphone, and from the microphone, you are unmuted. And so from that, it comes back to me, my speaker, it is blaring out loud and my microphone picks it up and that's a feedback loop. It's a full loop. And so that is what happens when you have this thing happen. What happens to the audio? It basically causes echo. That's what people typically refer to it as. I can very easily simulate that by just putting my microphone next to the speaker, but that's not the point. You know what an echo is in a video conference or any kind of phone communication, that you can see it happen. So you want to cut this, and that when you have this scenario, your output sound in your speaker that I create from my mouth into the microphone, it has to match what I speak. If I don't have that matching, then that is noise. So whatever I say should be clearly audible from this end, and it needs to match. If that's not the case, you have noise. Or if there's a feedback that goes like this, and then you have a loop that basically spirals around and the volume goes off. Off as in some squeaky sound comes out of the speaker that makes people think that it is causing feedback, causing echo, all sorts of noisy situations happen. Basically, it is not tracking or not matching what I am saying. And that's the goal defeated. So a feedback loop basically leads things astray. And that is what is attempted to be corrected by creating two different DQNs, is what this DeepMind paper describes. And so this is what is a short summary of the same idea in the paper that DeepMind has about using two different DQNs. One is called online DQN. The other is called a target DQN. And you periodically copy parameters from here to there, and thereby cutting the possibility of a feedback loop. which effectively leads to a situation which goes astray, does not get the result you want, and basically diverts the game to a wrong direction. Effectively, you don't accomplish the score you want to get. In a gameplay like that, in a Pac-Man game, you want to maximize this score. In an audio-video conference, you want to make sure that your person who says something is heard properly, and it needs to match. If that doesn't match, you have a feedback loop going. And that is what you want to cut. And you cut that by either asking the other person to mute, or using echo cancellation software, or separating microphones and speakers. So keep them separate. Speaker is away from mic. That's a very easy solution to keep them just separate. So some separation here, or echo cancellation. Echo cancellation idea is quite similar to this idea of your online and target, two DQNs. Now, in the example of echo cancellation, what happens when you have a person, say, speaking in a mic, and what you do is you might see that this sound can travel to the other person's speaker, and the other person is unmuted, so the microphone picks up, the speaker comes back, the audio comes back, this spoken word comes back, and it comes out of the speaker. And so what you want to do in an echo cancellation is you say, send this signal, let's call it signal S over as function of time. And that signal transmits, goes down, gets picked up, and you want to capture this signal, and you want to, whatever you receive from here, you don't want to send it again. So the moment you send, that completes the loop. So in an echo cancellation system, what you want to do is calculate the negative ST. So whatever, if you send a function ST, you receive some slightly similar function back. And what you want to do is to actually put a negative sign on it and reduce from the actual function. So if this feedback will be captured no matter what, and it will cause a loop. So in your pipe that travels, in the pipe that is making your sound travel, you're sending ST and S prime T as received from the other end. So S prime T comes back from this microphone and is sent. So what you want to do in echo cancellation is basically have another function that cancels out like this. And so on the wire here, you have ST plus S prime T minus S prime T, effectively canceling these out. That's the idea of echo cancel. So you have a separate circuit dedicated to calculating the inverse function of the incoming echo noise, and you cut it out. That's a separate circuit deployed in an echo cancellation setup. That is exactly conceptually similar to this idea when you have two DQNs. And what you're doing is correcting on a regular basis, correcting the parameters from what the actual scenario is, which is the actual gameplay is, onto your DQN calculation so that your feedback loop is cut. That's the underlying concept. Again, there are very different examples, but feedback loop in a classic echo cancellation system operates conceptually same way. You have two circuits dealing with one with amplification, one with noise cancellation or echo cancellation. And this echo cancel is basically a simple negative sign. This is what echo cancellation actually does. It basically flips the incoming signal from the other end and subtracts it before it is sent, so that the effective signal that goes on the wire is actually minus S prime T. And thereby you suppress or cancel out the echo to some extent, not to a great extent, but to some extent. That's why you still have occasional echoes. So that was about why we have two DQNs. Now in our example, this creates, by the way, two DQNs. So in this example, you will see that we will define a function that creates two DQNs. So this Q network creation is actually a function. So from here all the way to this point is just a function definition that creates a DQN, or rather a Q network. And you will see that in our notebook here. So this is your queue network definition, and we will use that function in here. So create a queue network, create another queue network. This will be called your online network. This will be called a target network. You're using this function 2 times, 1 and 2, to create 2 different identical networks. And feeding your input, and you have a method to copy your parameters. So this is your copy operation. Copy from online to target. That's the copy operation as invoked in this TensorFlow action. This copy ops is basically target variables assign online variables for all the target variable items. So basically you are iterating through the target variable items, and for every target variable in that target variable dot items, which are the parameters from the online network, you are copying it over. And so you will see the expression here evaluates your parameters from the online DQN. Let's erase my blue ink, and I'll proceed forward a little bit. And let's see if we can execute parts of this. So I'm going to execute also as we go along. So we'll go to this step, reset the graph, and execute that portion. That sets it up. Okay, I think something is missing. TF is not defined, so we have to go back a step and import TensorFlow. So we have to begin from here. So creating Pacman environment. Then build DQN. TF is not defined. Where are we invoking TF? Okay, somewhere ahead, I guess. There, import TensorFlow. This is your cart poll, Markov chains, Markov decision process, and Q-learning, and then this Pacman. And I executed that picture. We now build DQN, and this should not error. Yeah, it did not. So that import TensorFlow was missing in our previous step that was necessary for us to define this and the function that we have defined. We have 2 DQNs defined, and we will see the next now that we can actually go forward with it. So next ideas we have are our online variables. From the online DQN, we want to see what are we dealing with. So we can see what online variables not defined. Oh, we did not run this step. This step, and then the online variables. Then we are setting up our problem. In here, we are going to train the network. So we are specifying a learning rate. We are also using a momentum parameter for momentum learning, using the momentum optimizer, using the momentum functions. Nested of equals true. That's a nested of optimizer you may have seen in the past in earlier examples, in earlier chapters. And we want to optimize minimize the loss function essentially. So this width function, the width statement will help us in the training of the DQN that we have specified. We'll initialize and save. There are some variations between what the book has and what the notebook has. The first versions, if you have an older book, there is some variations in the way this is described here versus here. We will clear the ink and execute this portion. I just hit execute on a bunch of steps, and we can, of course, now the main training loop, and the training has started. So we'll see, you can interrupt the cell above any time to test your agent using the cell below. You can run the cell again, it will load the last parameters. So this is a breakable training in a sense that is a good thing. So let's also examine what is the CPU doing at that moment. So CPU seems to be busy, about 40–50%. Okay, leave it running there. Let's see what we are running right now. We have a class defined here. There are 3 classes defined in Python. One is to replay memory class, the append class, and a sample class. So 3 class definitions. We are setting replay memory 500,000. And this replay memory will construct using this class. We are also defining another function called sample memories and epsilon greedy, another function. And then the actual training step is running, which is what I just executed. Oh, we're not there yet. So there are more. I think this is a checkpoint definition that they have created here to help us with ability to break the training loop and interim evaluate is where this checkpoint function comes into play. So you can skip and resume training. A few variables for tracking purposes, game length, total maximum Q, mean max Q, and loss functions defined here. Now the main training loop, which is what is running right now, we are establishing a session, inputting a file location for a checkpoint function, and then initializing, copy online to target, and then while true. It's an infinite loop with a break involved. So we'll break when the number of steps reach the pattern defined, which can be a number up ahead somewhere. The number of steps should be defined here somewhere. How many steps we have? N steps. Where is the N steps definition? I need to search. It's such a long code. Okay, come on. Search for N steps. Where is the N step defined? Come on. Not here. Should be above. This number should be defined somewhere above. There, 400,000. So it's a long training loop. Total number of training steps. So when the steps grow beyond, we'll break. Iteration, basically step by step, one at a time, so many number of times. And print. So the iteration printing is happening right now, I think. That print action probably is happening, as we can see at the bottom of this. Yeah, it has done a bunch, 1,200 and so many out of 400,000. It's not 400,000, it's 4 million, is it? Yeah, it's 4 million. Yes. Wow. So 4 million times. We are trying to estimate loss and mean max Q value and the iteration number right now. And training steps happening. So in our sequence, what we are looking at, in the sequence that the run sequence that is happening. The printing step is what we just observed here. If done, which is when the game is over, start again, and you have to keep playing the game so many times for the machine to learn how to play. Online DQL evaluates what to do. Then online DQL actually plays and then memorize what happened. Compute statistics for tracking purposes. They're not shown in the book, but they're here. If iteration is less than the training start or iteration, this is basically getting us the ability to only train after the warm-up period or at regular intervals. We sample memories and use the target DQN to produce the target Q value. And so the idea of using the second network here comes into play. Train the online DQN, which is where we are estimating the loss function, and we want to optimize around that to loss value. That's the optimization that we are trying to train on. At regular intervals, we'll copy the online DQN to the target DQN, that is this action. Copy online to target, that's a function we have defined above. And save regularly. So if you break this, we can, of course, save the state on the checkpoint path. So it says you can interrupt the cell anytime to test your agent using the cell below. You can then run the cell above once again. It will load the last parameter saved and resume training. So now that we have like so many steps, about 0.1% of the overall game training portion of the game, or rather training portion of the algorithm, 0.1% finished, we can probably stop this and break the run right now. So here we go, break it. Break. That should break. Come on, interrupting the kernel. So this training broke. Is that the right way to break or not? I don't think this is a keyboard interrupt we just sent. I don't think this is the right way to break it. But maybe it's the only way to break it because there is no other way to break. I guess the break the kernel is the, maybe I interrupt the kernel is the only way to break. So it breaks, but it does create errors in the keyboard interrupt errors because we broke. Thankfully, we have saved at least we have a function that saves. Now, whether it's saved or not is a different thing. Here we have something saved in the checkpoint path, which saved the state of the learning at the time before the break happened. So with that break in our hand, we can see whether we can animate something as we have seen. So we'll see whether we execute this function, which should actually attempt to animate. And plot animation is not defined. Where? I thought we defined it. Plot animation. Oh, since we broke the kernel, we have to run through all of these steps? I don't think so. But maybe that's the case. So plot animation is a function defined up ahead. Where is that? Pre-processing, plot animation. Let's go to the top and maybe go all the way through the top and make sure that we correct that function definition. So stepping through this, OpenAI Gym, we look for the plot animation function. Plot environment function right there, but where is the animation function? I think it's probably with the cart pole. I think that's where we plot the animations first time. So that's where the function will be defined, I guess. There it is, plot animation function right here. This function. We need to make sure that we have it. And now it is able to plot the animation as you see in this example. But this is not what we wanted to run. We will go down and actually execute our 2DQN setup. So we will go here, these actions, we'll pick them up. And we don't have to build the DQN again, or do we? I don't want to take chances. So I'll just skip the training part and use the save state from a previous run. And so this is the training about to begin in that 43, step number 43. That's where the actual training happens. So we have interrupted that. We'll now skip through that training and go to this step to see and we get another error. Plot animation not defined. I thought we ran through this. Plot animation we ran through here. Like that. Did we? Plot animation. Okay, plot animation defined. Let's go down. And show me some animation, please, to see my interim 0.1% run. And plot animation. So there it is, some animation happening. This is a very, very small portion of the entire training, but it does show us some animation based on what the training has captured from the checkpoint from my DQ1 setup. And that's what you see, that it's basically going to go round and round and behave like Pac-Man does, and it is playing, and it will eventually die. That I think that's the extent of capture we have in the game. But if you let the whole training succeed and then plot the animation, you will have a full game, a winning game as envisioned by these guys in DeepMind. This requires a lot of practice to get to a point where we can actually apply this to a new setup. This is the area of current research and cutting edge implementation happening in automotive cars, by the way. Learn by, so drive by wire. The idea here is drive by wire. That just like in Boeing company, you have this thing called fly by wire. Now we already know this thing. The idea behind drive by wire is this concept very, very similar to what happens in a plane. You have a car from Tesla or Waymo or a bunch of other Uber, or I don't know who else is, Rivian. These companies are making technology. They're using these kind of same techniques, like we have discussed just now, which is to basically enable drive by wire, hands-free, total control, go from point A to point B, take the person, take the car, travel, and you see observations coming from all over, on the front, on the side, behind us. And so that's the input, and ultimate accomplishment is travel, successful and safe travel. That's the goal. You want to take actions along the way. In case of actions, there are more than 9. There are tons of actions you can take. You can accelerate, brake, turn your steering this way, turn your steering that way, back up, go forward, turn left, turn right, a whole bunch of things. There are more than 9 actions. In a simple Pac-Man game, there are only so many actions. 9 actions in a simple game like Pac-Man. In a car, tons of more actions. So that means you have to basically look at every component in the car will produce some signal. And so that signal needs to be accumulated. So you have, car will have, let's see, if this is the car, and this is the front of the car and the back of the car. You have a camera here. You have camera here, maybe more cameras, I guess. I think there are 16 or 17 or some cameras all around the body of the car. One looks around, one different fields of view. And so these cameras and other sensors are centrally connected to 4 different computers within the car. These 4 computers themselves are 10 gigabit gigabit internet, 10G Ethernet connected. And they are running the same algorithms. The challenging part with a car setup is that there is no, or rather not much not much high speed internet on the body of the car as it travels. It may not have internet at all, actually, but you still expect the car to drive without internet. It might have some signals like 4G LTE signal might be available to the car, but that's very narrow pipe. So it cannot really rely on external internet-based, cloud-based CPU horsepower or GPU horsepower. It cannot rely on that because the bandwidth is very narrow. And so that's ruled out, primarily ruled out. You can use that internet access to push data out to improve upon further iterations of the software itself. So when software updates comes down, that's an iteration of the software. It learns better ways of handling. But as the car operates, it has to basically collect data from various cameras and various other sensors, proximity sensor, things like that are not visual in nature. Those sensors, like whether the battery is heating up, or whether the brakes are going down, that you're wearing out, or you have the tire pressure. So you have 4 tires, 1, 2, 3, 4, and the pressure in the tire is going below the threshold that you expect. So there is pressure sensor. We have available charging sensor. We have things like, if this is the battery of the car, then I'm just drawing it like a battery, but the battery of the car is a different style. If the battery is running out and running low, you need to take special actions and basically let this car be driven to the nearby charging spot so you can charge the car. And the only action at that time when the battery is running really low is to guide the driver or guide the passenger, or just if there is no driver, just take the car to the nearest charge spot and charge first before you even travel. Because if you travel without a charge, you get stuck and then you're dead in water, or maybe not without water, dead in the middle of the road. And so that's the kind of setup that these car manufacturers are dealing with these days in terms of understanding how do we take input. In the trivial example that we just saw, like the one that is described here, the example takes a very, very simple input, which is basically some pixels, like 160 by 210, 3 channels, pixel input, and you have 9 actions to take, and then you accomplish a score. Whereas in a car scenario, there are hundreds of sensors, probably more. I don't know how many, maybe thousands. I'm just making stuff up. Many sensors basically, and they are sending input. Some of them are visual, like the camera channels. Others are not visual. They have some other information, and the actions you can take are also definitely more than 9, and the inputs are way, way larger, and you still have to accomplish a result. The result is safe travel from A to B on a map. Safe. And also fastest, given speed limit and given other law. And so we have to basically travel from A to B. That's the goal. And given these actions you can take, and you want to optimize around these results. Now the classic thing that I think Elon tweeted, and there is maybe not Elon, somebody else tweeted, a big figure in this game of creating a car like this, people who are building such things, or people who are creating these new machines that will help humanity in some sense, actually in a big sense, if they make a mistake, if the people make a mistake in making this car, then Tesla is killing people. Simply, it's such a hard job. People will start saying Tesla kills people. That's the problem with this kind of a function from a human perspective, or I should say, what's the word for it? Yeah, I don't have the word for it. So it has not. It's not a technical word. It's a psychological word. So I'm missing on it. But the idea is the job that these people who develop a car for Elon is a very, very hard job. If they do a absolute perfect job, 100% score, no mistake, zero mistake, then what happens? People will say, like, the world will say, meh, yeah, it is technology. It is expected to drive perfectly. What's the big deal? Yeah, you made a zero mistake and you collected in basically made sure that you made a perfect car that drives from A to B. And it does. And it does with 100% reliability, by the way, with no accidents, nothing like that. So you made zero mistakes. And the response from the community at large, the world will say, meh, yeah, you did your job, whatever. It's actually such a hard job to accomplish, to make absolute zero mistakes at the end of the game. The game is when you travel from here to here. And when you do such a job, the reward a human developer, the people who are developing these cars with Elon and others, the reward is very poor. Okay, yeah, the car went from here to here, no mistakes, no accidents. What's the big deal? Technology is supposed to do like that. That's the reward. It's very unfortunate. That's the problem that I think is a psychological problem. But this is not about psychology. They're not, the people who are developing these technologies are not really worried about the end result. What they really want to do is actually accomplish the goal. And they're doing it. They will do it. You will see success here. Absolutely, you will see success. The problem is hard. You will see success. In the process, yes, there will be mistakes, unfortunately. And this might happen, but that is a very, very less likely to happen compared to the other option. So what's the other option? Is people drive cars. People drive cars and they go from A to B, and every day there is some accident somewhere. This is the alternative. The autonomous alternative A to B will also have mistakes, but they are likely to be less than this. And even if there is a tiny, tiny mistake, people will complain Tesla kills people, or the autonomous car company kills people. People killing people, people are okay with that, apparently. People kill people, people drive bad, and people die. That's probably okay, apparently. But this, not okay. Even though this is less likely to kill than this. It is statistically less likely. And that is just the nature of things that you can actually measure. So this is less prone to accidents. This is more prone to accidents because people are involved, and that's a given. That's the nature of the problem. And I think the people who develop this are not really worried about this May problem. No mistakes, big deal. You made a car that works with no mistakes, big deal. Wow, technology is supposed to behave like that. That's the classic psychological problem, but leave it aside. People who are passionate about these things will keep on developing techniques. So let's do a quick recap of what we have been discussing in this deep learning thing. Basically, deep learning is a layered structure of calculating an output based on an input that you provide with a goal that may be different. So this output is then going to be an action that you take, and you want to optimize on some goal of some sorts. Problems of these types, you've seen variations of it in convolution neural networks, which take a classic input as an image, a IMG input. So basically, it's very, very nicely applicable to scenarios where there is visual input. The second technique that we saw was the long short-term memory, or also known as recurrent neural networks. And those are applicable when there is a sense of time involved, like a series of data involved, series of data of some sorts, data like spoken words being recognized, or things of that nature, or stock price movements, or any sequence that is based on time. That's where recurrent neural networks come into play. We talked about autoencoders, which is a fascinating way to actually help us with any of these, the fully connected neural networks, convolutional neural networks, recurrent neural networks. We have autoencoders that we discussed just a few days ago, which actually helps us in identifying features that are relevant, dropping features that are not relevant, and also helping us in all these other techniques in terms of improving upon what we already have in terms of application of these technologies to a given set of problems. And then we are discussing this one, which is what we did today, was about reinforcement learning, which is basically on a, think of it as a gameplay where you take an action based on some input that you receive from a variety of sources, and your ultimate goal is to optimize on some parameter somewhere. And that's the idea behind reinforcement learning. This field is also evolving, and you will see much more evolution coming up. And I will, the evolution you will see. This, by the way, this deep mind thing is as late as 2017, and we are in 2018. So evolution is expected. No doubt it will happen more and more faster. And by 2020, you will see more automatic vehicles on the road, more automatic drones in the air. Unfortunately, that sounds scary, but you are likely to see it, at least in some experimentational scenarios, depending on how the law evolves. But that is absolutely happening, and you will see it coming. The training part gets slow because of our laptop or desktop or whatever you have. So if you run this on a proper machine, which is what I plan to do, is I plan to run this Pacman thing on a cloud GPU based machine to see how it performs. And that's what I will be doing sometime when I find some time. So I will be focusing on that. If I find a good functional demonstration, I'll ping you. And that is how I plan. I also want to tell you that I want to thank you very much, Troy. I want to thank you because you have helped me tremendously. I don't know that you know this, but I want to say that. I'll tell you how you helped me. Sorry?
Thank you. It's been a great experience going through this.
Let me tell you how it has been great for me, and I want to tell you how you helped me. I want to take the time. So what happens is when, in any new thing that people create, like I am creating this machine learning AI bootcamp, right? It is new. You know this. We did it first time with you. And, 5 years ago, I started the cloud bootcamp. Same thing. First time when I ran it, there were literally 4 people in the program. So it's a small program. That's how it begins. And, when the number of people was 4, then the next time there were only 2. And at one time, there was only one guy, just like your situation. You have one person. We started the boot camp with like 3 or 4 people at the first day. The very next day, 2 guys drop. I think one guy drops and the one guy says, I'll come later, and then he disappears. Those people in Poland disappeared because I think I think this program is too mathematical in its nature. So that's the challenge.
Yeah.
It is math oriented. And so there's no way to escape that math. I try to tone it down to basically simplify as much as I can. But this is what happens as you start something new. You have to start small. And this grows over time. I've done these kind of new things in my life so many different number of times that I'm comfortable with the idea of one person joining, like totally comfortable. You would not have probably thought that I will actually run through the entire program with one person. But what happens when you run through the entire cycle? Let me show you what happens. So here is what happens. Now I have in my machine learning bootcamp segment all these videos.
Yeah.
Right.
Yep.
So you have the video recordings. So you have access to it. I have access to it. And now the fact that I have done it once, I can say, very, very logically, I can say and claim that I have done it. That's one big benefit. So like next time I can say, yes, it is not new. It is an existing program. Please come and join. I can show them these videos that I have. I've collected them. I'm going to open them to show people, hey, you want to see it? Go ahead, see it. So that people get an idea about what this thing is about. And since I have done it already once, I have learned a great deal, probably way more than I expected to learn by doing it for real. And that means my next iteration is going to keep on improving. This will improve over time. This happens every single time I do something new. I keep on improving and refining, and I will, create something, that fits into the sequence of. We have 16 sessions. So my program, I think 24 sessions, maybe. I don't know how many extra days we took, but whatever. I just told you I will take whatever time it takes to finish this, and I did. And I will probably try to fit it in the sequence, or what I have observed is that in the first run, I was a little slower compared to my usual Cloud Bootcamp speed is very high. So I will probably learn from this, which I have, and speed up myself. So that will shrink. And I'll have to come up with the exact number of sessions I need for the next iteration. Now, maybe I'll expand the program a little bit, or shrink it, or cut some, add some, bring some new examples, and read more academic paper to bring in more ideas. This, by the way, is a good book.
Yeah, and the new version is available on Safari right now, at least the first 9 chapters.
Is it?
Yeah.
I did not know. So the first 9 chapters, so new version, as in version 2 of the book, or what?
Yeah, it says it's going to be released next year.
I see. I should go subscribe to Safari. So the book that we have here is the version I have. Can you compare the version, please, for me?
It says it's 2019. I don't have it up right now. I was looking at it yesterday.
Here. This is what I have. So what do you see in Safari?
They had a draft version, and it only had 9 chapters. It didn't do TensorFlow.
Yeah, because TensorFlow 2.0 is coming next year.
Okay.
And so that is what the book is going to be covering in June 19. And so that's the new book that will eventually show up. So it's a pre-order available. The first 9 chapters are actually not TensorFlow, right? If you look at chapter 9 here, it is TensorFlow. So that's what you will see, is that the first 9 chapters are not TensorFlow, because TensorFlow is updating. And so those chapters will come later. The first 9 chapters are kind of sort of similar in that there is not much evolution.
Yeah.
But the later chapters are going to be different. And that's what I think he's writing, this guy, the author. And so that's what you will see. So now some questions for you. Honestly, how do you think we did? Was it useful? Was it good? Was it bad? How was it?
I like this. And having the code available on Jupyter was really helpful to be able to go off and just run this stuff while you're going through it and kind of run it in parallel while you're talking. I found it really helpful to have another laptop running that I can go and execute while you're working on your stuff. So I thought that was pretty good. That's a major help to, it's almost like a coaching mechanism that it's out there running parallel.
Right. So what should I do differently? Like, what should I do to improve?
Well, the pacing is probably the thing to figure out, so we don't go a month over expectations. But I have to say, in the beginning, though, I thought it was okay that we were going through it kind of line by line because it really helped level set everything for what we were going to do. And I'm not sure I would have had the same appreciation for when you speed it up later that I could follow because I knew what we were doing because we'd covered it so deeply earlier.
Right. The initial things, I think, especially chapter number 2, is kind of a nut job because it has to be done properly. Like this end-to-end project, you have to really go line by line to understand, because then once we understand what's going on, we can speed up. And that's what I found.
If you could summarize, I'm trying to think on this, whether you could summarize it and go through it fast and then come back to it. Because sometimes it seemed like I could get lost with, like, we're on step 5 and I wouldn't quite, see, I hadn't seen the whole run through yet. So it was almost like it wasn't that much of a help doing it for the first time all the way through because I didn't know what it was.
Okay. So begin with the summary first, then run, and then summary again.
Yeah, possibly.
Okay. I got it. I will do that. I think this is the rubber meet the road project that is necessary. Everything else, once you go through this, is easier to understand.
Yeah.
Makes sense.
Yeah.
What else would you like to tell me?
But it was a great foundation for the rest of it. It was hard to get through initially, but it got me learning how to execute the Jupyter and, going back and forth and being able to follow along with the class at the same time. So it's mostly the steep learning curve going into it. But once you get through that, it's okay.
Yeah, the learning curve is steep. No doubt about it.
Yeah, it is.
Yeah, it is deep and steep, I should say.
Yeah.
Okay. So we should coffee. We haven't met. So let's find a time and we get together and say hi to each other in person for the first time.
Sure.
You have had the I should say I have inflicted myself on you twice.
For 6 months of 2018.
I know, 6 months of me yapping. Oh my God. But that's fun, I guess. Fun that glad that you are able to tolerate me. I'm happy that you tolerated me, and I'm happy that you helped me learn. And so I want to thank you.
Well, thank you.
I will like to buy you lunch, not just coffee, but lunch. So pick your time, pick your date, pick your place, and let's go do lunch or something that you find convenient. Send me a time on text message or phone or whatever, email.
And are you normally based on the east side?
I am in Sammamish.
Okay. Yeah, I'll be on the east side next week, but then I go down to South Park for the break at Boeing. So I don't know if you want to do it this week or when we come back from the holidays. Kind of busy.
I'll let you decide. I'm here, and I'll let you decide. So, but basically, I have nothing else going until 21st when the boot camp starts again. So I'll let you pick and choose the date and time. My location is. Let me show you where I am. This is the blue dot you see. That's where my location is.
Okay.
That's my location.
All right.
So any location wherever you feel like is. I know your office in Bellevue is somewhere here. I think, where is it? Your Bellevue office, I think here.
Yeah, right above New. Yeah, right there. Yep.
And so I can, make it convenient to you. We can eat here, maybe eat here, depending on whatever places. There are places in Issaquah, the places in Bellevue.
Sure.
And so I'll let you pick and choose, and we'll just go there wherever you want us to go. We'll get together and grab, and you pick a date and time, and we'll go there like that.
Okay, that sounds great.
So thank you again. Thank you very much. And I appreciate that. Thank you
Yeah.
for helping me learn. That's how I would say.
Thank you. I'm not sure I can direct as many people into this course or not because everybody's scared of the math.
I didn't hear the last sentence you said. Everybody's scared.
Everybody's scared of the math. It's hard to like say, hey, there's militias in our course, and they're like, how much math is it? I'm like, oh, it's a lot.
I know math is a lot, but yeah, I try to reduce the math to the greatest possible.
Oh yeah. I didn't think it was a hurdle. I mean, it wasn't like
I think it is important to understand the math, if not at least, if not doing the whole math, at least understanding it is important. And so that was my goal to begin with.
Yeah, I thought it was great. I thought you did great with it.
Thank you, sir. I have emailed out dates for the future program. If you can please send it around to your friends, that will help. And so thank you very much. Appreciate that. And I look forward to seeing you in person for lunch.
Thank you so much.
You're welcome. Bye-bye.
Bye.